Hello, and welcome to the last section of notes for this unit. It is Units 3, and I believe it's the fifth section of notes. So if you do not have your note packet, you might want to stop the video and go grab it now. While you're getting your note packet, you want to be looking for Radioactive Decay, which is halfway through notes 4, and we're going to start talking about that. So I will pause for a second while you go grab your notes, and then we'll get going. All right. So as we learned about in the last unit, or last lesson rather, we learned about fusion, we learned about fission, and we briefly mentioned alpha, beta, and gamma decay. So we need to talk a little bit more about alpha, beta, gamma, and alpha, beta, and gamma decay, and how we work with them and what they can do for us or against us, I suppose. So in alpha decay, it gives off a positively charged particle that's called an alpha particle. But in reality, it's the same number of protons, neutrons, that a helium atom would have. So a lot of times we refer to alpha decay as giving off a helium atom as part of its decay process. Then there's beta decay, which will give off a negatively charged electron. And in the process of giving off a negatively charged electron, something else happens. And that something else is that a neutron is converted into a proton. So there's some energy given off there. And then lastly, the last type of decay that we are going to be concerned about is gamma decay. And that gives off high energy electromagnetic radiation, which we really haven't discussed yet. That's in a coming unit. But we talked about on the last video that it gives off a photon of energy. And we'll talk about what that means at least a little bit more going forward. So we have the three different types of decay, and we're going to talk about them in a little bit more detail, starting with the different radiation and how easily or not easily they can pass through different materials. So here we have a pretty decent infographic about how we can stop, or how penetrating rather, each of the decay particles is. So an alpha particle is relatively low energy. It does not travel very far, and it can be stopped by something as thin as a piece of paper or your clothes. A beta particle has a little bit more energy, and it can travel through things like paper or clothes. It can sort of go through your hand or part of your flesh, but it kind of gets stopped there, and it really gets stopped by something as thin as aluminum foil. But the difference is that aluminum atoms are a little bit more densely packed together than, say, paper or your clothes. And we're not really talking about the neutron in this particular unit, but the neutron is a little bit more penetrating. And then the higher, or the most penetrating of the particles, is the gamma radiation, which is again that large packet of energy that's given off by an unstable atom. And what happens is that can travel through paper, it can travel through your flesh, it can travel through metal, it can travel through water, but very thick pieces of concrete can stop it, and really dense metals like lead can stop it. So here's a little bit of food for thought, I suppose, when talking about the different types of radiation. When it talks about ionization ability, is how quickly that particular particle can become an ion. And then how penetrating is the revert is how deep it can, or what it can go through. So the alpha particles can ionize relatively easily. The gamma particles generally don't, but the gamma particles generally have more energy, and the alpha particles have a little bit less energy. Now, does that mean that alpha particles are not harmful, or gamma particles are the only thing that are harmful? And the answer to that question is no. They're all pretty harmful. It just depends on how those particles get into your system. So, for example, Even though an alpha particle is pretty easily stopped by like paper or clothing, if you happen to inhale an alpha particle, or you swallow something that has alpha particles contained in it, or you have a wound or a cut and the alpha particles are landing in the bloody area, those alpha particles can go directly into your system and cause a lot of damage. Beta particles, if you are in the presence of a beta emitter for long enough, you can get something called a beta burn, and a beta burn is simply a burn on your skin, um, and it can be really painful, and it can cause something called acute radiation syndrome or acute radiation poisoning syndrome. Um, but generally, beta radiation is most harmful when it is um, inhaled or swallowed or absorbed by the bloodstream in some way, shape, or form. And then we have gamma radiation, which is the most penetrating of the three different types of radiation that we're going to talk about. And what it can do, or what it does, is it travels directly through your body, but in the process of traveling directly through your body, it can lose a little bit of its energy. And sometimes when it loses a little bit of its energy, the fallout or the consequence of that is it can uh, disrupt or change your genetic structure, that is your DNA, especially in high producing or fast producing cells. So it can change things like because your skin cells are constantly dividing, so it can change the DNA in your skin cells and give you some skin issues. It can also affect things like your reproductive organs and the um, fast reproducing cells within there. So that's why it's really, really important that we are aware of the alpha, beta, and gamma radiation. One of the things that's important to note, though, is that alpha, beta, and gamma radiation poisoning don't generally occur unless there's some major incident or something or some consequence of some action that has occurred. So, for example, we generally don't see a lot of this type of radiation poisoning unless, like, we talk about Chernobyl or the reactor that failed as a result of the tsunami in Japan, or even things going back to as far as the bombs that were dropped at Hiroshima and Nagasaki. So those are incidents where we see a high um, consequence of the radiation poisoning, but most humans will basically go through their entire life and have very little effects of radiation poisoning at all. So here we have an example of uranium-238 undergoing something called alpha decay to form thorium-234. So the parent nucleus, or nucleotide, as it's sometimes called, starts with having enough protons and neutrons to give it a mass number of 238. The alpha particle is emitted, and the daughter nucleus, that is the nucleus that is the result after the alpha particle has been removed, is no longer 238, but it's 234. And if you look on the periodic table, you would locate element, let's see, thorium is number 90, and it would be right around 230 something in terms of its mass. So that's what happens with alpha decay. And so here are some chemical equations, or some alpha decay equations that go along with that. So if we start with an element like polonium, which is element number 84, if polonium undergoes alpha decay, it would give off the equivalent of a helium atom in terms of protons and neutrons. And then you would be left over with the element lead. So like the mass, the atomic number has to be the same value on both sides. So the fact that we have 84 on the left side of the arrow and 2 plus 82 on the right side of the arrow, that checks out. And then the mass number also has to be the same value on both sides. So we have 210 on the left side, and we have 4 plus 206 on the right side. So those balance out. Another way to write that, although not a little bit less common, I suppose, is that to put the 4/2, the mass number of the alpha particle, over the atomic number of the alpha particle, and then just write the alpha particle symbol. But for the most part, I think most scientists and chemists and physicists will just write helium. So down here, the information on the bottom is just talking about the fact that as you go from left to right, the amount of mass number on both sides has to equal, and the amount of atomic number on both sides also needs to be the same. Then there's beta decay, and during beta decay, it's not really easy for us to illustrate how it happens, but basically what you do is you take a neutron and you convert it into a proton, or the unstable atom has enough energy to make a neutron into a proton, and that energy that's given off is then given off in the form of that negative electron. So in the case of iodine 50 or iodine 131, what happens is that one of the neutrons is changed into a proton. So the mass number doesn't change, but in that process, the number of protons now increases by 1, which I get is a little bit confusing because the notation right here indicates that you'd almost lose an electron, or I'm sorry, you'd almost lose a mass number. My bad. One more time. We'll try that one more time. You lose an atomic number, but the reality is that you're not losing a proton, or you're not losing an neutron. You're simply losing a negative electron in the form of a lot of energy. So the big thing that you have to remember about beta decay is a conversion of a neutron into a proton. So what happens is that the mass numbers will stay the same, but the atomic number, will increase by 1. Okay. So that's just something that you're going to have to remember about beta decay. And then the last type of decay is gamma decay. And here we have a nucleotide, or a nucleus rather, that is formed and it's in an excited state. That is, it has a little bit of excess energy to start with. And when it has a little bit of excess energy to start with, that energy has to be given off in order for that particular atom to go back to its not excited state or its ground state. Sometimes I think of the excited state of you're in your ground state most of the time, but then somebody gives you a whole bunch of candy and you get a little bit of a sugar high and you're flying around and you're acting all silly, and then you eventually go back to your normal self. So the ground state would be how you are normally, and the excited state would be after you've eaten like a bunch of sugar. So I like to think of this particular example as cobalt having eaten a whole bunch of sugar, and it has to get rid of that sugar somehow. So it gives it off in the form of gamma radiation, and then it goes back to being normal cobalt. When we talk about gamma radiation, though, there is no change in mass number. Note that the mass number, the 60 and the 60, are the same on both sides, and there's no change in atomic number. The 27 and the 27 are the same on both sides as well. The only difference is the loss of actual energy. All right, so here's some practice that we need to talk about for a second. The first thing you have to do when you're looking at these is you have to identify whether or not alpha decay or beta decay is going on. You probably won't see anything with gamma decay, in large part because gamma decay is pretty simple. It's just a little change in energy. So what I'm looking at here on the first one is I see that there is no original or parent atom, but I do see an atom or an element and another element on the other side. But the dead giveaway here is that helium is present, and helium as a product is a general giveaway that alpha radiation is occurring. So if you have helium as a product, it's alpha radiation. So I'm going to say that this is alpha radiation. And alpha radiation means that when we're going through this process, that the mass number has to be the same on both sides of the arrow, and the atomic number has to be the same on both sides of the arrow. So if I take 205 plus 4, so let's see, 205 plus 4, that gives me 209. So that's going to be my mass number on my reactant side. And 82 plus 2 is 84. That's going to be my atomic number on the reactant side. And if I locate element number 84 on my periodic table, I see that element number 84 on my periodic table happens to be polonium. So then in the next example, I see that I have samarium and what appears to be an electron. So remember, the dead giveaway that beta radiation or beta decay is occurring is the presence of an electron on the product side. And so what we have to remember about beta decay is that a neutron was changed into a proton. So the mass number, so this is beta decay. So the mass number will be the same on both sides. So 147 must be equal to 147. So I'm going to have a mass number of 147 on the top here. And then the bottom, though, is going to be an increase of atomic number. So I'm going to go from 60 something, in this case it's going to be 61, to 62. So this original element had an atomic number of 61, and if I locate 61 on the periodic table, I see that it is element promethium, which has the symbol PM. And there you have that. Why don't you take a second and pause the video and work through the next two here, and then we'll check our answers. Okay. So in the case of the next one, 255, 99, arrow something to what appears to be electron, that tells me that electron is a dead hint giveaway that it is a beta particle that's being emitted, so it's beta decay. And I also need to remember that the mass number is going to be the same here, so 255 will equal 255. So I'm going to put 255 right there. And I also need to remember that the atomic number is going to increase by 1. So if I have 99 here, that's going to become 90, or it's not 99, it's going to become 100. So that means that my atomic number down here will be 100. And if I locate element 100 on the periodic table, I see that it is fermium, or elemental symbol Fm. The last one was alpha decay again. And I knew it was alpha because of the presence of the helium. So we know that the mass number and the atomic number values must be the same on both sides. So if I have 31 on the left side, something plus 31 must equal, or something plus 31 must equal 4, or I'm sorry, so 31 basically minus 4, wow, words are hard for me this morning, is 27. So that's going to be my mass number, 27. And 15 minus 2 is going to be 13. So that's going to be my atomic number. And if I go to the periodic table and I see that aluminum is element number 13. So there you have it. So those are your 4 alpha and beta decay practice examples. The last bit of information that we need to talk about here is just a brief summary. So here we have alpha decay, where A is the mass number and Z is your atomic number. It undergoes in alpha decay, a helium atom is given off, and the mass number minus the helium mass number and the atomic number minus the helium atomic number will give you your new element. Beta decay is the emission of an electron, but in the process of that, the proton is, or a neutron is being changed into a proton. So the atomic number, the Z number, will go up by 1, but the mass number will stay the same. And gamma decay, you have an atom that's excited, It's had too much sugar, it gives off a little bit of energy radiation, and it goes to its ground state. So the other way to look at it, which I think is a pretty decent part of this chart right here, is that as you do alpha decay, the mass number is decreased by 4 as you go to the product side, and the atomic number is decreased by 2 as you go to the product side. In the beta decay, the mass number is unchanged and the atomic number increases by 1. And in gamma decay, the mass number and atomic number are both unchanged. So that kind of makes you a little itchy because you kind of forgot. Sometimes mass number is known as A, and sometimes atomic number is known as Z. Okay. So if you have any questions, make sure that you get a hold of your chemistry teacher. Otherwise, I believe there is a summary activity that goes along with this in your note worksheet packet, and check it out. And like I said, good luck and have a good day.